So picking up with example D, you have 250 feet of fence to enclose a rectangular pasture at the edge of a river. What dimensions of the rectangle enclose the most land? So here's kind of a nice Desmos look at what's going on here. So you can have kind of a very narrow and deep plot of land, or you could have a wide plot of land that's not very deep, but somewhere in between is probably going to be the happy medium. And if you look down here at this function a of c, you can kind of see that, all right, you know, it's getting bigger and bigger, smaller. So somewhere around here is about the best we're going to do. So the question is, what's the exact dimension that maximizes that area? So once again, another optimization problem. We've got our picture, and let's try and label this a little bit. What do you want to label where? You've got 250 feet of fence, but what do I want to label where? How about if I call that an X and call that a Y? Okay. They don't have to be the same. They could be the same, but in general, they're not. So we can't say that this is X and this is X. That's not the way it works. Picture function. Well, we're trying to maximize the area. So what's the area? How do I calculate the area of this rectangle?
X times Y.
X times Y. And I'm just going to write area there. Until I can write this as a function of one variable, I'm just going to write area there. And, well, I seem stuck. I mean, how do I get rid of the Y? I don't know that Y equals sine of X like it did in the last one. So what could I do? Generally speaking, well, we'll do the interval after we get the function. But generally speaking, mathematicians don't waste words. And in particular, one of the things that you could notice in this problem is that they told us that we have 250 feet of fence. We haven't used that yet. So let's see how we can use that. Well, how would you calculate how much fence we're using here? Sort of the perimeter, as you would say. What does that 250 have to equal?
2x plus
Let's be careful. 2x, even though it's not written, it's understood that there's another x over here. It's 2x. How many y's? Just one y, because this side is the river. So 2x plus y. So that gives me a way to solve for y, to get rid of one of the variables. I'll rewrite this as y equals 250 minus 2x. And now I can plug that into my equation up above. Plug that in here. And that gives me, we can call it a of x, because it now depends on just that one variable. A of x is x times 250 minus 2x. So yeah, that's looking pretty good. Now you can distribute that and whatnot, but let's see here. Let's worry about the interval. What's the interval? What's the smallest that x could be? 0. Should I actually include 0 or not? Should there be a bracket or parenthesis there? Ethan's shaking his head. Parenthesis. Yeah. If it's a 0, then you've got 0 area. So that's not really going to help out much. On the other side of things, you know, what's the most that x could be? Not quite 250. Because 250, that's how much you have for all the way around. If you shrink this down almost all the way to nothing, so that you're really making a very narrow and deep kind of rectangle here. So like this, you're getting closer and closer. If y is getting closer and closer to 0, then the length of these sides has to be getting closer and closer to their maximum. So the largest it could be, largest each of these sides could be, would be 125. Because if you had 125 here and 125 here, you're using all of your fence for the depth and none for the width. So 125 is going to be the most that we have here. And if you set this equal to 0 and find the roots, you'd also see that from this term right here, the maximum that x could be and still be positive would be 125. So 0 to 125, that's your interval. The analysis part is going to be kind of pretty simple compared to some of these other ones. This is 250x minus 2x squared. Let me bring that over here. Minus 2x squared plus 250x. And of course, the only arrow in our quiver right now is to take the derivatives. And that's not too bad. Negative 4x plus 250. I want to know whether that's equal to 0. That's going to be when x is 62.5. 250 divided by 4. Someone double check me on that. 62.5. And that would be units of feet. How do I know that this is the actual maximum and I didn't get a minimum instead of a maximum? How could I tell? How would you tell? Yeah, second derivative is going to be pretty easy on that one. Here's the first derivative. What's the second derivative? Negative 4, which is less than 0. So if it's less than 0, then what kind of a shape does it have to have overall to the graph? Concave down, right? So the shape of the graph has to be concave down, and in particular, any critical point would have to be a maximum. So by the second derivative test, a double prime, or excuse me, a of x has a maximum at x equals 62.5. Now I think they ask you for the dimensions of this box, not just define the box, but what are the dimensions? So I need to know x and y. So the dimensions would be x equal 62.5. How am I going to find y? Yeah, plug it in. 250 minus 2 times 62.5 is going to be 125. So there's your dimensions. Width and height, or width and depth, depending on what you feel. Well, let's put in the proper notation for feet, and we're all set. How's that one looking? Okay? All right. Let's try a couple more, and let's see which one's next. Ah, the Norman window. You know, I've talked to architects, and I've not found too many that have heard of a Norman window. But what a Norman window is when you put a semicircle on top of a rectangular base. So let's take a look at a little Desmos thing here. So here's your semicircle on top of a rectangular base. You have 30 feet of perimeter to enclose this window. Now within that 30 feet, you can make it wider and shorter or narrower and taller. But here's how things change as you change the dimensions. And at some point, you're gonna kind of run out of room. You're not gonna have any more material to make it bigger or make it taller. So in some place in between, you're gonna have to find your happy medium. So let's see if we can do that. All right, so let's take a look at example D here, or example E, I should say. Example E. And I'm gonna cheat. That looks pretty good. And draw this down. Okay, so let's start with our picture. We've got a semicircular top on top of a rectangular base. Let's define a few things. Let's say, and it's up to you. Do you want to call this distance here X, or do you want to call it R? If we're coming up here, if we're thinking about that distance up here, then you might want to think of that as being the radius. I get it, that's fine. Or maybe you're just more comfortable using an X. But one way or another, we've got to start labeling some distances. So what would this one be? You want to use X or R? Preference? R it is. All right, so that's an R. And I got an R here, although that's in yellow because it's not really material that I'm going to use. And not much else I can label. I gotta have something for this side here. So let me call that one Y, just for the moment. We're gonna have to come up with something to put in there for Y. We know we have 30 feet of perimeter. So that's something we're gonna use. Let's write that down. 30 feet equals the perimeter. Peri meaning around, meter meaning distance, so distance around. 30 feet to use for this. Let's work on our function. Now the function that we eventually want to maximize is the area. We want as much light coming through this window as possible. So let's not try and do everything all at once. This is probably the biggest challenge of you in doing these problems, is to get this function that you're going to maximize or minimize. So the area is going to be made up of two parts. It's going to be the area of the base, plus what? Area of the semicircle. Okay, looking good. Let's see what we can do with this. Now the area of the base, we got to be a little bit careful. R is just half of this distance, right? It's not the full distance across. So you've got basically the full distance across would be 2R. I'm just using R because it represents the radius, and that'll help us out up here. So the area of the base, let's put that one in terms of R and Y, is going to be 2R times Y. Now I need the area of a semicircle up top. And conveniently, we've got an R here already. What's the formula for the area of a circle? Pi r squared. So pi r squared. But I don't have a full circle, do I? What do I got? Half of that. So let's put in 1/2. And let's still just call this the area. It's not a function of one variable yet. Let me pause. Are we okay with what we've got so far? What information haven't I used yet? Something that I'm going to need because I need to get rid of the y here. Yeah, I haven't used the perimeter yet at all, have I? So the perimeter was 30 feet, and that 30 feet is going to be the perimeter of the rectangle. Perimeter of the rectangle plus the circumference of the semicircle, or half the circumference of a circle. Which one sounds better? Circumference of the semicircle. So let's see if we can come up with some expressions for those. Now when you're coming up with an expression for the perimeter of the rectangle, keep in mind I want this side, and this side. I'm not going to use the top because that's just open space already. So what expression should I put in here for the perimeter of that rectangle? 2r plus 2y. Good. Now let's switch over to the circumference of this, or half the circumference of a circle. That's going to be 1/2. And the circumference of a circle is given by 2 pi r. The 1/2 and the 2 cancel each other out, so you get 30 equals 2r plus 2y plus pi r. Now what? Where am I going with this? Solve for y, thank you. Need to get y by itself, so I'll move these terms of r over the other side. 30 minus 2r minus pi r equals 2y. If I divide everything by 2, let's see, I guess it doesn't really, let's see, we'll do 15 minus r minus pi over 2 times r equals y. So a lot of work to get this down to a function of just one variable. But this is my expression that I'm going to substitute for r. So how are we looking with that part? Now it's going to make our formula a little bit on the messy side. That's okay. Let's substitute that in here and see what we can come up with in terms of a variable or a function that just depends on one variable. It's going to be our a of r equals 2 times r times 15 minus r minus pi over 2 times r plus 1/2 pi r squared. So not exactly the friendliest of formulas here. It's okay. I'm sure we can struggle through. Picture function, then what? Joey? Interval. We need to figure out an interval where this is going to be defined on. And I'm not going to bend my mind to it too much. I know that it has to start at 0. You can't have a radius that's less than 0. Even equal to 0 doesn't really do us much. And then I've got 2r. Well, I've got a total of 30 feet to work with. So I can't have too much, especially if I've got 2r. If I do 2r this way and 2r this way, still have to have some up here. So let's see, 30 divided by 2 would be 15. If you just wanted to make this as small as possible, that would be a decent interval to look at. Certainly you're not going to be looking beyond this. If you wanted to think about this more carefully, you could probably get that down to 10 or lower. I'm just trying to find a decent upper limit to think about. I'm sure that our value that maximizes this is going to be a lot less than that. So let's turn our attention to maximizing our function then. A of r is 2 times r times 15 minus r minus pi over 2 times r plus 1/2 pi r squared. That's our function. We want to try and maximize it. So this is the analysis part. It probably makes sense to me to distribute that 2. That'll make our work of finding the derivative a little bit easier. So a of r is going to be 30r minus 2r squared minus pi r squared, because that 2 and that 2 will cancel. So pi r squared plus 1/2 pi r squared. I'm not sure if anyone sees it, but do you notice that there's like terms here? These two. Minus 1 and plus 1/2 gives me a minus 1/2. So again, making our life of finding the derivative just a little bit easier. 1/2 pi r squared. The 2 and that 2 cancel.
I mean the one right now for the negative 2r squared minus pi r squared.
So we combine those two. Where are you looking though?
The negative 2r squared.
There's 2 with the r squared, but one's a pi and one's a 2, so you can't really.
Yeah, you could factor out an r squared here, but 2 and the 1/2 pi, I mean, it's kind of tough to do those. So you could, if you wanted to, you could write this as 30r minus, say, let's see, 2 plus 1/2 pi times r squared. You could do that, but I'm probably just going to differentiate it from here. Let's find the derivative. So a prime of r would be 30 minus 4r minus pi r. And I want to know where that's 0. That's going to be my critical points. Let's see. I'll move these two terms to the other side. That's going to be 30 equals 4r plus pi r. Any suggestions why I moved those two terms to the right-hand side? Why didn't I just move the 30? Yeah, so moving it to the right-hand side, when it changes sides, it changes signs, and it made those positive. I encourage you to try and avoid negative numbers as much as possible. So I'll factor out the r. That leaves behind 4 plus pi times r. Divide both sides by 4 plus pi, and there's your answer. Now, how do I know that that actually makes this a maximum? I'd probably go to the second derivative test, because the second derivative test is going to be easier than plugging this in, evaluating it to the left, and evaluating it to the right, and getting the sign of the first derivative on either side of that. Rachel, what's the second derivative of a?
It would be
Here's your first derivative.
negative 4 minus pi.
Cool, negative 4 minus pi. And what do I know about negative 4 minus pi? it's always less than 0. What shape does the function have to have then? What shape, concave up or concave down, does a of r have? Concave down. So therefore, a of r is always concave down. If it's concave down, then this point has to be a maximum point by the second derivative test. So therefore, 30 over 4 plus pi is a max by the second derivative test. Okay, now that's the radius. I need to figure out what y is. Now this is the radius. It'd be nice to know the dimensions of the height as well. So let's see if we can't figure out that. So the base is going to be twice that. Let's figure out what y is. I'm kind of curious about that. For that, let's bust out our graphing calculator. I don't think we want to do this one in our head, and I don't think the algebra is going to be all that friendly, so here's my suggestion. Let's take 30 divided by, say, 4 plus pi, and store that in x. So to store, you're going to hit the store key and store that in x. And now I want to calculate my expression for y. Going back to my previous page here, we got y was 15 minus r minus pi over 2 times r. So let's plug that in. Except we're going to use an x as opposed to an r. 15 minus x minus pi times x divided by 2. And there you go. Interesting. So the height and the radius are the same. So the height is about 4.2. The radius is about 4.2. R equals 4.20. H equals 4.20. The base, remember, is twice the r. So the base equals 2r. And the height equals 4.2 as well. Let's see, just 4.2, yeah. Yeah, so the dimensions do have this kind of strange symmetry that the base with the radius is the same as the height. Nice. And I'm not sure what base or dimensions to list for the top part of it, but it's a semicircle with a radius of 4.2. So we're in good shape. All right, that was a long one. Thoughts on that one? Don't worry, I don't put any more than 8 or 9 of these on an exam, so should be okay. Let's do a couple more examples. I want to finish out 3 more examples. Let's see. Do you want to work on one? Or do you need some guidance? No confidence? Want to try one? All right, so this is a decent one to work with. Now, in thinking back to some of our previous ones, what we've done in several of these is in getting your function, you start out kind of at a high level, and then you realize, oh, wait a minute, I've got too many variables. And then you have to use some of the other information that the problem gives you in order to find a function of just one variable. That's gonna be true with example F as well. So we're gonna try and find the volume of a box that, let's see, square base must have a volume. I wanna find the dimensions that minimize the amount of material used. What's the amount of material used gonna relate to? Well, it's gonna be the bottom, and then the four sides, and then the top. So keep in mind that one of these is gonna have a dimension of y, the other two have a dimension of x. And they give you that you're using 4,000 cubic centimeters, or you're gonna enclose 4,000 cubic centimeters. Okay, good luck on that one. Let me put my pause button here. Help each other out. I'll walk around and try and help out as well. Picture function interval analysis.
She's leaving her Chester fries on. That's like really dangerous.
You can help each other out. You don't have to just sit there and work on your own. You can help each other out, that's fine. Trying to minimize the amount of material you use. So that's gonna be the area of all the sides, the top and the bottom. So we are gonna use the volume, but it looks like you're starting off trying to find a volume formula. And that's not what we're gonna need.
No, because the top's gonna be all of it. That's actually
So we were
That's why I was so confused between.
How many of those sides do you Four. So the 4x1 would be the area of all the sides. 2, and I'm not gonna count the top and the bottom. 4x1 plus.
There's four,
something else.
so you need all four because all sides. Yeah. And then you're adding in the area.
Oh,
But then you just have to make it.
good to know.
I did that too.
Thank you.
In terms of x, so. Not very good.
And I use the volume to figure out what y would be. You use, so we start with this, right? We don't know what y is, so I use the volume formula to figure out
figure out the inner line.
It's base, this stuff doesn't have this basically, so it'd just be like y times x. So that would mean y would equal this.
Talks about the amount of material used to construct that office.
Yeah, you can solve it pretty much.
We need to get rid of that one, I think it's. That's what it is. This is the area of the side. That's the one. I thought so we should get used to.
Finding the dimensions, right? So what we have.
Call it area there.
Right, find the dimensions of the box that minimize the number. So we're trying to calculate the areas of the materials, we don't know material issues, right? So we're not providing the tops, we only need the base and the floor sides. So that's why
So we're trying to find something minimizing the material,
is 4,000.
which would be the area of all
So
sides.
that has to be 4,000 each.
So how do you find the area of all sides?
So my that's the volume.
That
So it's X, Y.
volume, so when you supplement your volume is given,
Right.
like that.
But that'd be different than X, Y,
That's what I'm
power, 4 times X, Y, 4
Because
times.
that would be the only way you can relate the volume to that.
Does that make sense?
Unless there's an
Then you
easier
got a
way.
bottom and a top.
I think that's
I'm trying to make it.
Because that's the volume of the.
Now, unfortunately, this depends on 2 variables. So that's where you have to reach out and look at the problems here, what information have I used yet?
I'm trying to.
So I gotta find y.
Yeah, you gotta find something then be able to solve for what.
I don't know, it might be like that again.
I've got this thing so far.
Find the dimensions of the
Area. So we're finding the dimensions. So the dimensions would be an area. This is what I got so far. Squares.
So I.
Now this one's open, so you don't need this one. Just have 4 sides and 1 base. The base would be the x times.
And then I got y equals 4,000
Here's how I found the
negative
x.
2.
And you have 4.
And then I did the surface
And then
minus
you can plug in your y
squared plus 4y.
That inverse.
And then I
What's the area?
and then I factored that out.
So you get a negative if you take the derivative, but I haven't gone any further, so maybe you'll find out here.
But I don't know that.
So I
No, that's just the area of the sides.
I just.
And you got top.
I got the start of it, I just.
And together,
Like,
that'll give you the area of the whole.
it could be
So why is.
Oh, well, that's the volume.
But if you think about it, you got an X, you got a 4XY, that means your area of
That'll get
the
wide.
function needs to get
And that makes sense.
fine tuned a little bit, so that
The base is x by 9.
just depends on
So
the
the
variable.
volume.
And that's where you're gonna go back to the problem,
You have your
no.
to solve for y and
Both of
y.
them.
It's a function of x.
Well, then you got one.
So is that?
Yeah.
Yeah, that's the
Oh.
parameter.
I think I might have misled somebody, I didn't realize that this had an open top. So,
Yeah.
as far as the top is concerned, you don't have to account for any material there. The bottom does have some material.
Oh wait,
Yeah,
yeah,
it'd be
that's
a plus,
right,
yeah.
okay, okay, now I see where. Thank you.
So, yeah.
And then.
I gotta change all of these now, yeah.
That's it, right?
Does it make sense so far?
Yeah.
Yeah,
Yeah, so you-
yeah, I gotta.
So you solve for y, you plug it in there.
For the area at the bottom.
Yeah.
Oh no, clean that up,
Yes.
because one of these X's will cancel.
and I had to use the product rule
4,000.
because of the,
Yeah.
well, I changed it to 16,000 x to the negative 2 times x. Like, does that make sense?
Yeah.
And so then when I did the product rule, I did f is 16,000 x to the negative 2. F prime would be negative 32,000 x to the negative 3.
It looks good so far.
X2 prime.
I
So then
don't have the answer memorized, so I don't know. But if you're looking like you're heading in the right direction.
Yeah.
Well, it doesn't really matter.
One of those X's will cancel.
I shut it off.
Oh, okay, okay.
Yeah.
My bad.
Like you could put it, you could call it M if you want. It's just like, if I was.
Can you just solve for y?
You know,
Good.
the only one you can use is X and the Y ones, because those are.
What's the area of the bottom?
You know what I mean, like variables.
X squared, x times x, not like 2x.
So,
You distribute.
Yes.
You just get it.
Yeah, distributed forward.
I don't know what the domain, like, would I just do 2,000?
0 to infinity. There's no, I don't think there's any.
Cause the limit,
maximum.
right, like there's no,
Yeah, I don't think there's any, no maximum.
okay,
But then the x's will cancel. So you'll just have one x's.
Okay, so I guess what you're discovering for yourself is these things are fun and amazing. Let's take a look at how this one would be solved. So we've got our picture already drawn for us, that's nice. Let's work on the function part of it. So, let's see here. As far as the function is concerned, I'm gonna wanna find something that talks about the area. So maybe I'll call that S for surface area. It's gonna be the area of the four sides plus the area of the bottom. And the area of the four sides, well, any one side like this one is just gonna be x times y. And I've got 4 of those. So it's gonna be 4xy plus the area of the bottom, which is x squared. So that's S, the surface area. But I need to refine that a little bit because it's got a y in it. I need to get rid of the y. So then you look back at the problem and realize, oh, I haven't used this information yet. So let's do that. The volume of the box was 4,000 cubic centimeters, and that volume is going to be x times y, or in other words, x squared y. If I solve for y, I get 4,000 divided by x squared equals y. And I could plug that into my equation here. And let's see, one of the x's will cancel. Let's just do that. So it's going to be 4x times 4,000 over x squared plus x squared again. I'll end up with 16,000 over x, or I'm going to write it as 16,000 x to the negative first. So S of x equals 16,000. That x will cancel. That x in the denominator I'm going to bring up as x to the negative first plus x squared. Yay. Now there's no real nice, easy bounds on x, other than to say x has to be greater than 0. You can't have a negative length, you can't have 0 length, otherwise you won't have anything there for your box. So my interval, as far as that's concerned, would be 0 to, well, infinity. You could make this really, really big, but really, really short. So 0 to infinity, that's the interval I want to look at. Let's find the derivative here. So a prime, or it's going to be s prime, I should say. Where'd it go? Not finding it. That's all right. Oh, here it is. So s prime of x is going to be negative 16,000 x to the negative second plus 2x. And that's going to equal 0. Now, a couple ways you could solve this one. Let me try and take my time a little bit more with solving it so that way I give you something that is useful rather than anything else. So this is the analysis part. S prime of x is negative 16,000. X to the negative second plus 2x equals 0. You might want to do this. Write this as 16,000 over x squared plus 2x equals 0. Most of us don't like equations that involve fractions, so to get rid of the fractions, you could, anyone fill in the blank? Yeah, multiply by the lowest common denominator, in this case, x squared. So that x squared has to distribute itself to this term, and this term. Now, of course, the right-hand side is pretty simple. That's just going to give me a 0. Here I get a 2x cubed. Here I get negative 16,000. If I move that to the other side, 2x cubed equals negative 16,000, or positive 16,000 now because it changed sides. X cubed equals 8,000. I'm guessing that x equals 20. Nice. Don't forget to look back at what the problem's asking. I know at this point you're like, yay, feeling really, really triumphant. But as far as the dimensions are concerned, we need to figure out what our y dimension is. We know that y equals 4,000 divided by 20 squared, which is 4,000 divided by 400, which is 10. So the dimensions overall are 10 by 20 by 20. I probably should double check that this point is actually a minimum point. You could do that with the first or second derivatives. I'm not going to take the time right now because we got 2 more problems to do to get done with this. Comments or thoughts on this one? All right. Let's move on to example G. We got 1, 2, we actually got 3 more problems. What do you think? No, I don't want to try and keep you for 3 more problems. We're going to cut this video into 3 pieces. So let's take a break.